Hello everyone, I hope you all are doing well. This side Priya Bhatia. And in this specific video, we will be discussing about the maths behind SVM, support vector machine. If you remember in the previous video, that is the introductory video of SVM, we have talked about a lot of stuffs. We have seen that SVM is a very widely used algorithm because of its handling power of outliers, because of its handling power of nonlinear data distributions as well, with the help of a kernel trick. I have also talked about the major objective of using that kernel trick, how basically it will be able to transform any lower dimension data, which is very impossible to classify, to a higher dimension, and then trying to get that hyperplane. Yes, hyperplane is something which I feel is something new for you all. And today in this specific session, we will try to discuss the maths behind that hyperplane. What is the equation of that? We will try to derive that, right? Because this is something which is very, very important to understand. And then maybe in the upcoming session, we will be in a situation where we will try to see the implementation of whatever stuffs we have learned so far. So without wasting any time, let's get started. So whatever things we have explored till so far in the previous session of SVM, we have seen that, whenever we are talking about a higher dimensional space, what we are looking in a SVM is a hyperplane, right? That's what we had a talk, right? For example, let's say we will be having a line, and for example, this is the line, and there is one line above that plane and one line below the plane. And we have discussed that this is something, the gap is called as a margin. Let's suppose we have one class category lying over here, right? And we have another class category lying below, right? Let's suppose this is the another class category which we have lying somewhere here, right? Now, what we want at the end of the day in our model is to create a best decision boundary, right? Is to create a best, you can say, model which will classify the data points in an appropriate manner, or if it's a regression task, is to give us an appropriate point, right? Right? This is the actual need of whatever task we are doing. One thing which I have not talked about in my previous discussion, and I was genuinely want to talk about that, but I forgot to talk, is the support vectors, right? So the name itself is support vector machine, right? So what is the meaning of support vector? If you will be able to observe this line, which is above hyperplane, which I'll say it as pi plus, let's say positive class and negative class. So if you will be able to observe that this line will be drawn in such a way that it will be having a very closer distance between this point and this line, almost equals to 0. Same thing happens in the pi negative as well. The distance between this point and this line is almost overlapping. So this kind of points are called as, you can say, support vectors. That's the very first thing you have to understand, that these points which I am encircling in the orange color is called as a support vector points. Always remember. That is why the name also is given as support vectors, right? Now, if you will be able to observe that if we are talking about a higher dimensional space, maybe 3D, 4D, or ND, right? If let's say we're talking about 3D space, 4D space, 5D space, till let's assume ND space, right? In any of the spaces, what we are looking for is a hyperplane, so that we will be able to classify our points in a very beautiful manner, right? By the way, this is something which we call it as a margin or the distance d, and task is to maximize that so that there will be no overlap between the 2 points and the classification will be done in an appropriate manner. Now, if let's say it's an equation of a line, if we're talking about a 2D space, you all know that the equation of line looks like y is equals to mx plus c, which in other form, in general form, we can write it as, I think in the last session also we have discussed, ax plus by plus c is equals to 0. If you have to compare this equation with the above equation, and if you want to try to find out the value of m and c, what you will be able to get, or the value of y. So how can you write this equation? You can say by is equals to negative of ax minus c, or in other words, you can say y is equals to minus of a by b, x minus c by b. So can I say that this m somehow signifies the value of negative of a by b, and c signifies somehow the value of negative of 1 by b, right? Y is equals to mx plus c. So if you compare this equation 1 and this equation 2, they are the similar equations only. The value of m here is negative of a by b, and the value of c here is negative of 1 by b. But in other words, I can say that I can write my 2D space, two-dimensional space, into this form, right? So what could be the equation of hyperplane is what we are looking for in today's session, right? So that we will be able to understand it very carefully, that how the decision boundary is being made, because this is something which we are calling it as a decision boundary, right? And you will be able to observe that the distance between this to this and this to this is almost equal, right? This is actually in the exactly middle point. Maybe visually I can't make that, but I hope it is clear till so far. Now, if I want to find out the equation of a hyperplane, so we know the equation of a 2D space, but what is the equation of a hyperplane? You must have, somehow intuitively find out these kind of equations in your lower classes, but I don't know how many of you remember that. So we will try to do this part, okay? Now, if let's say the same thing I have to represent in terms of w and x, so that the confusion will be less when we will go to the higher dimensional space. So can I write like this? Can I write like this? w1 x1 plus w2 x2 plus I'm representing this intercept, which is c, as w naught is equals to 0. Can I say this is the equation of two-dimensional space, right? Now it will be very easy for you to understand. How? If let's say I have to write the same thing for a three-dimensional space. So you know, when we're talking about 3D space, we will be having 3 points, which is let's say x1, x2, x3, right? So in that case, what is the kind of equation you will be able to get? w1 x1 plus w2 x2 plus w3 x3 plus w naught is equals to 0. Can I say this would be the equation of a three-dimensional space that we will be having, right? So in this manner, you will be able to form an equation for n-dimensional space as well. So if I'll ask you, what is the kind of equation you will be able to create for the nd space, for the n-dimensional data points if you will be having, what is the equation you will be able to get? So your answer could be that, Priya, what I will do is I'll say w1 x1 plus w2 x2 plus w3 x3 until I'll keep on adding until whatever be the value of n I will be able to get, plus w naught, which is the intercept, is equals to 0. And this much part is very much apt. Now, in this specific use case, if you will be able to understand till so far the kind of equations which I am writing here, right? How I have written? I have just used this equation and I have tried to write this down into a more generalized manner so that we will be able to understand under all the higher dimensional spaces as well. Now, can I write this equation? This equation is nothing but, can you say it's a matrix multiplication? Can we write this in the form of a matrix multiplication form? How can we write that? So can I say, I hope you all know how can we do a matrix multiplication, right? So if I'll just try to create a vector of this where I will be having the points w1, w2, w3, w4 till the value of wn, and another vector column wise I will be having, let's suppose the values are y1, not y1, x1, x2, x3 till the value of xn. So can I say that this is something that we have as a same thing which we have written here? So this part, maybe equation number 3 you can say, and this way of representation is also same, because this above equation is nothing but is a matrix multiplication of w vector and the x vector that we have plus the value of w naught is alongside we have. So can we write this as a dot product, which is w into dot product of x plus w naught is equals to 0? The same equation number 3, I'm writing it in the form of a dot product. So this basically represents a matrix multiplication. So if you will be able to observe, if you want to multiply two matrices, this is how multiplication will be done. Taking row wise, column wise, and adding all of the values we will be able to get. So w1 x1 plus w2 x2 plus w3 x3 till the value of wn xn. Perfect. Now in maths, mathematical notion, we can write the same thing. Can we say like this, w transpose into x? So we can write the same thing of w into matrix multiplication with the x as w transpose x plus the value of w naught that we will be able to get is equals to 0. And this is something which is the equation of a hyperplane as well, right? Hyperplane as well. So be it whatever dimensions you are in, this is a kind of a equation which you will be able to form, right? So here you will be able to see that what is happening is you will be having this equation, which is a decision boundary of w transpose x plus w naught is equals to 0. And you will be able to observe that the values which lies above this plane is nothing but w transpose x plus w naught. The value should be more than equals to plus 1. And here the value will be w transpose x plus w naught less than equals to minus 1. Now, how is this plus 1 and minus 1 boundaries are being generated as a pi plus and pi negative? I will try to showcase you everything. Just wait for a few minutes. You will be able to understand everything here. So this is the equation of a hyperplane, first of all, which we will be able to get. And now, if let's say our data point of w transpose x plus w naught is bigger than equal to 0, it means that somehow the point lie above positive class. And if it is less than that value, means the point lie below negative class, right? For example, I'll just try to showcase you visually that what I'm trying to convey here so that you will be able to understand. But what I'm trying to say, let me first of all write it down and then I'll try to showcase you visually. I'm saying that it belongs to positive class somehow if the dot product plus w naught is equal to bigger than equal to 0. In that case, it will lie above that decision boundary. It's a positive class. And if it is less than, in that case, you will be able to observe it belongs to another class, which is minus 1. And that is how basically the complete classification of SVM is being done. What I'm trying to showcase you, just wait for a while. Let me just try to showcase you few stuffs here. Maybe what I can do here is I'll use one platform called as, you will be able to see, desmos.com, which basically used to give me a graphs of whatever things I really looking forward is. So for example, if let's say here I'm just removing all these stuffs, you will be able to observe, let's say we will be having equation like 2x plus 3y minus 3. Usually in a two-dimensional space, it's very, very easy to understand, right? If let's say I will provide you some value of x and y, which is a bigger values in a way. In other words, I'm trying to convey, if let's say the value of x and the value of y is equals to maybe 2, 3. So what you will be able to observe, if you will enter this specific data point, so let's assume this is a new set of points that we will be having. Now I want to see that whether it belongs to a positive class or it belongs to a negative class. So what my model will do internally is, it will try to refer this set of points in the main equation, try to check whether it plots above this line or below this line. So what will happen is, in other words, it will, for example, we are taking 2, 0 as a label, which is a new set points. It will try to see this line lies, this is a, you can say decision boundary, which you are trying to classify, which is 2x plus 3y minus 3. Now, if it is a point, which is 2, 3 as a new set of point, you can say it lies beyond that line. So it will be classified as positive label. But on the other hand, if let's say you have a new point by the name of minus 2, 0, which lies below that, so in that particular, say you can say it's a negative class. It belongs to a negative component, right? What I'm trying to convey here, for example, if you will be having a point which lies bigger than equal to 0, what does it indicate? This is the genre. So if there is any data point which lies above that or beyond that points, all those points will lie in the somehow positive scenario. Otherwise, if you will be able to see if the value is less than 0, you will be able to see it lies below that line, and that's the main reason it will lie as a negative class This is how basically the classification will be done, where we will be having some standard equation, and if the point lies above that decision boundary, it means it belongs to a positive class, otherwise it belongs to a negative class, right? So this is what the main cost function you can say, which basically helps the SVM to decide that whether it belongs to a positive class or a negative class, or class A or class B, and will help my model to determine that how the classification between the two set of points will happen, right? This is the major important parameter in the SVM, right? So here, if you will be able to observe, this is the main part which you have to understand, that is the equation of a hyperplane. And now I think if you will be able to understand this aspect, you will be able to see that in the upcoming session, when we are doing an implementation of this particular thing, so you will be able to see when we're talking about a classification task, we will call SVC. The full form of SVC is support vector classifier. Now I think you will be able to understand what is the meaning of support vector and why it is classifier, because the internal cost function which is associated with that is a classification task. And if you want to do this regression kind of a task, there is a separate model altogether by the name of support vector regressor, right? Support vector regressor. So be it any kind of scenario, you will be somehow solving the equation of either the classification task or the regression task. The only difference is when we're talking about a regression task, our target is not +1 or -1. Our target is somehow the continuous values, and the cost function will get changed to again that R square value, that MSE score, which we already have discussed in our previous sessions whenever we have discussed about the regression based scenarios, right? But this is the literal maths of designing a hyperplane or decision boundary in such a way that it will be able to do an appropriate task depending upon what kind of problem statement you're trying to solve. Kernel plays again a very important role in the complete maths of SVM. You will be able to observe major role of kernel is to determine a higher dimensional space. If my data is in a 2-dimensional space, our model will try to convert it into a high dimensional space till the point where it will not be able to create that decision boundary, that hyperplane, so that the classification will become very, very easy, where we will be having almost all the points which are positive classes above the hyperplane and negative classes lower the hyperplane. I hope now that image which I just showcased in the previous video will also make more sense. By default, we have RBF, right? You can understand the depthness of that RBF. It's a radial basis function. We have multiple functions in SVR, and we will try to apply, you can say grid search CV or randomized search CV to determine that which particular kernel fits the best. You can see that we will be having a linear kernel. Linear kernel means logistic regression only, sigmoid function, which we have discussed, 1/1 plus e to the power minus x, right? Polynomial, RBF, sigmoid, pre-computed. Yes, sigmoid you can see, right? It is already mentioned. So you will be able to see, depending upon what kind of data we are dealing with, we will be applying that kind of a kernel. But by default, it is RBF only. Degree is 3, degree of the polynomial of a kernel function. By default, it is 3. All these, whatever, apart from that parameters you are saying, for example, gamma, coefficient, the value of C, the value of epsilon, shrinking, you will be able to observe that all these are the parameters which are basically useful in terms of the functions that we have. For example, if you will go to the maths of this, you will be able to understand the complete idea behind these coefficients, right? You will be having a different functions. For example, polynomial kernel, how it looks, what is the internal function of that, kernel stats, radial basis, function network, everything is available on Wikipedia. If you want to explore in more depth, you can explore. As of now, I am skipping that maths because if I'll try to go in that much depth, again, it will be, might be for few people, it will be too much and it might not be that much required for the ML per se. But yes, if you are curious to know that what is the maths behind all these functions, it's a mathematical per se mode, then I would suggest you all to go and check out the Wikipedia pages. It's wonderfully written. What is the cost function we have, how basically it will look like, how the graph will look like for for the similar kind of a function. Everything is available. So explore and do your own research on top of this. So now I hope that you will be able to get a clear cut idea behind the equation of a hyperplane and how we can form that. In the upcoming session, we will try to discuss the implementation of SVM now, and how we will be able to optimize the hyperparameters of SVM via the grid search CV and randomized search CV. I believe this topic I have touched upon in random forest implementation also, but I'll just do a brief recap of that same part again, so that I'll try to showcase you that how can you implement the same algorithm of grid search CV and randomized search CV in the implementation of SVM as well. So stay tuned, and I'll see you all very soon in the upcoming video.